I'm a chemical engineer that works out of the Boston office of COMSOL, and I'm joined by my colleague Mats Nygum, the Technical Product Manager for COMSOL's Fluid Flow products. Mats is joining us from our Stockholm office in Sweden. He holds a Master's in Engineering Physics from the Royal Institute of Technology, Stockholm, and a PhD in Applied Mathematics from the Massachusetts Institute of Technology, MIT, right here in Boston. He has previously worked many years in industry simulating CFD applications, including ones that involve rotating machinery. We're very pleased to have someone of Mats' expertise join us today, and he also led the development of the mixer module. So we can go on to the agenda. This is today's agenda. I'll provide a brief introduction to mixing in general, and why simulations of mixers are of necessity to many different industries and applications. Mats will then take over and give a complete description of the mixer module, the functionality it contains, and how a lot of that functionality works. To illustrate the advantages of modeling mixers and using the mixer module to do that, Mats will perform a live demonstration where he builds a mixer simulation from scratch. After this, we'll answer your questions. So you can ask questions by typing them into the little field you have there as part of the GoToWebinar controls, and they'll all be sent to me to ask them up. You're more than welcome to type in these questions at any time through the presentation, but we'll get to them at the end of the webinar. And then we'll wrap up the webinar with some information on how you can go further. So before touching on the reasons for simulating mixers, I thought I would talk about simulating applications in general. Firstly, we at COMSOL believe that simulations give you insight into your application by providing an understanding of your device, such as a mixer. What we've found is that through this understanding comes innovation. Modeling and simulation also lets you propose some designs and then tinker or optimize with them. A lot can be considered and achieved before proceeding to the expensive stage of building prototypes or deploying directly to manufacture through using simulations. Finally, the real world may still be different than the simulations and prototypes would indicate. Working together with testing and manufacturing processes, simulations allow you to test and verify the quality of the component or process you're interested in, and indeed the mixture's composition that you are interested in. Now, during these webinars, we like to get a bit of feedback from those that are listening to us, and so we ask some poll questions. So let me just launch the poll question here, and you can all go in then and click for an answer. And the first question is, how frequently do you use a simulation tool, including Excel? Do you use it daily, weekly, monthly, or never? I'll give you all a few seconds to answer this, and then I'd like to show you the results. So now we're getting just about everyone there. I'll share the results with you. As we can see, we've got a few people here that are really into simulations, and they're obviously looking to see what the mixer module can give them to add to what they're currently doing. And there are, in fact, only 10% of you say that you never simulate. So we hope that you will actually get a lot out of this webinar here to see what it could do to help you with your applications. So why do we simulate mixers? Well, the simulation of such allows you to predict the fluid flow, composition, and temperature distribution in mixers and stirred reactors. But it isn't so much the manufacturers of mixers that are interested in simulating them. They could, I suppose, if they wanted to design different options or test different materials and the like. But modeling mixers is more for the people that would be using the mixers. This includes the manufacturers of fine chemicals and pharmaceuticals, consumer products, and in food processing. And when you're putting together expensive batch runs of chemical or mixtures, you're not so concerned with saving a little bit of energy consumption here or there. You want to be sure that the product is of high quality and is reproducible from batch to batch. A lot of mixture and chemical reaction simulations are done assuming the world is as predictable as you would see in a nice, clean laboratory. You're just simulating the kinetics, assuming the conditions of a perfectly stirred reactor, like in this production of ibuprofen. Here we can see the steady state being reached after a certain amount of time. But is this really reality of a mixer? You can take the next slide. Yet reality isn't a perfectly stirred tank reactor, and there are always the possibilities of dead zones or zones with little mixing, affecting the overall conversion and composition of the mixture. Here we see there is quite a lot of variation in the composition between the inlet and the outlet. Simulating a full model of the conditions in a possible reactor setup using baffle placement and impellers of a particular design will give you that much more confidence in the reproducibility of your mixture composition. Now let's go on to the next poll question. And that is, for what reasons do you currently use a simulation tool? Do you use it just to simulate reaction kinetics? Do you simulate CFD applications? Or do you actually simulate the Rodin phenomena that you get in things like mixers? Or you don't use a simulation tool at all? And so I'll just give you a few more seconds there to answer. And I can see that you're almost there now. So I'm going to close the voting and share the results with you. And here we can see that almost half of you here are interested because of the CFD abilities of the mixer module or something similar to it can give you. This is something that you would have expected, Matt, this stuff is divvy up between the different ones. But yeah. Anyway, it was definitely an interesting result.
It looks quite reasonable,
yeah. Great. Well then, with that in mind, let's see where the mixer module comes within our product suite. So the mixer module is part of the COMSOL Multiphysics suite, as you can see here. The whole suite is applicable for modeling many different applications from all fields of engineering and science. And the new mixer module is part of the Fluid series and is an add-on to the CFD module. Now at the top of the product suite, you can see the COMSOL Multiphysics base package. This is the engine for your modeling, including defining your own equations, meshing, solving, and post-processing. All of the modules contain user interfaces and predefined physics couplings for their specific application. For example, the CFD module contains physics interfaces for a variety of fluid modeling, like laminar, turbulent, and two-phase flow. And all the other physics interfaces in the other modules can be freely coupled to any of the others, such as the physics interfaces for solid mechanics coupled to a fluid flow interface in order to simulate fluid structure interaction. And you can expand your modeling by making use of the optimization and particle tracing modules, while the LiveLink products are great for integrating your modeling with the rest of your product development workflow. This includes importing and optimizing your CAD geometries and pre- and post-processing through using MATLAB and Excel. Now, I'd like to pass you over to Matt, who's going to go into the particulars of the mixer module and talk about the features and so forth that's contained in it.
Thank you, Phil. I'll tell you a bit about the capabilities and the functionality in the mixer module before we get to the live demo. For laminar flow, we can model Newtonian fluids and also non-Newtonian fluids with a power law model or the Carroll model. For turbulent flow, we have three turbulence models, the K-epsilon model, the K-omega model, and the low Reynolds number K-epsilon model. The last two are mixer module specific. Here you can see a list that displays the rotating machinery fluid flow interfaces in the mixer module. The rotating machinery interfaces combine rotating and stationary domains using a sliding mesh approach to account for topology changes. The interfaces have two study types, the frozen rotor study type and time-dependent. For the time-dependent flow, we can also model moving free surfaces with contact angles which depend on surface tension coefficients. Now, I'll go into a little more detail about the frozen rotor study type. It can be used to simulate rotating devices without rotating them. The rotating parts can be considered as frozen in position. So for cases when there is no topology change between the domains, it can deliver the exact solution, such as in this case here. And even in cases with changes in topology, we can get good approximations of average flow quantities, as we shall see in the live demo. A frozen rotor simulation can also be used to generate initial conditions for a time-dependent simulation. For incompressible stationary flow in a rotating frame, the Coriolis force and the centrifugal force contribute to the momentum balance. And the frozen rotor study type solves for the velocity in the stationary frame, and it effectively includes the Coriolis and centrifugal forces in the rotating frame. Between the two domains, the flow quantities are mapped pointwise. Here the boundary between the two domains is shown by this circular black line here. When it comes to mixer boundary conditions, assembly pair conditions are applied on boundaries between rotating and stationary domains to enforce continuity across sliding mesh boundaries. Rotating walls are automatically identified, and we have wall conditions on internal shells for thin immersed structures in order to avoid meshing thin regions. The thin immersed structures include rotating and stationary interior walls as well as screens. We can also apply periodic conditions for sector symmetry to reduce the domain size. I'll give you a little bit more details about the turbulence models as well. The K-epsilon model is a standard K-epsilon model with realizability constraints. We also have the revised Wilcox K-omega model, again with realizability constraints, and a low Reynolds number K-epsilon model, which is the AKN model with realizability constraints. The K-epsilon and K-omega models use wall functions to model the flow in the near wall region. The mixer module includes wall functions for both smooth and rough walls. And the low Reynolds number K-epsilon model, on the other hand, resolves the flow all the way down to the wall. One of the two exclusive multiphysics interfaces in the mixer module is the rotating machinery non-isothermal flow interface. Similar to the rotating machinery flow interfaces, it models laminar and turbulent flows, including fully compressible flow for Mach numbers less than 0.3, and in addition, heat transfer in fluid and in solid parts. The figure here shows a simulation of conjugate heat transfer in a dished bottom mixer with a helical ribbon impeller. The second multiphysics interface in the mixer module is the rotating machinery reacting flow interface. It models multi-component transport and flow in rotating machinery, including turbulent mixing and reaction models, as well as composition-dependent fluid properties. We can choose between Fickian and mixture average molecular diffusion formulations, and the Stefan velocity is accounted for. You can also include migration of charged species in electric fields. A convenient way to set up a mixer simulation is to use the supplied geometry components in the model library file modular mixer geometry. I will show you this in the demo. The file contains subsequences for building flat and dished bottom vessels with or without baffles and two types of impellers, the Rushton turbine and pitched blade impellers. In case the supplied geometry components don't fit your needs, you can always define your own components. Now, taking advantage of the multiphysics capabilities in COMSOL, you can extend your mixer simulations to include fluid structure interaction, conjugate heat transfer including radiosity and radiation in participating media, reaction engineering with surface reactions, or particle tracing. The model library models include the geometry components, model and mixer geometry, which is used by 3 or 4 of the tutorial models. There is also a non-isothermal mixer tutorial and a benchmark model called Power Law Mixer. Now let's move on to the demonstration. In the demo we shall first define a mixer using the supply geometry components. Then we'll set up the mixer simulation using predefined selections for domain and for rotating domain and for the boundary conditions. Then we'll import some post-processing variables, and finally we'll solve and compare the results with experiments. So now I'll switch to COMSOL. So we'll go into the model library, and here we find the modular mixer geom file. Now I'll show you these geometry subsequences. We have one that builds a pitched blade impeller, one that builds a Rushton turbine, and one for the dished bottom geometry, and one for a flat bottom geometry. And you can combine these in different ways. So if you want to change the impeller type to a pitched blade impeller, you just okay, something happened here. Oh. Okay, so now we'll build, here we go. So now we changed the impeller to a pitched blade impeller. We can change the vessel type to a dished bottom vessel. And we can change, for example, the diameter of the vessel. So there are a lot of possibilities here, and that you can explore. You can change the number of baffles, the diameter of the impeller, and the blade length, etc. So now let's start with the demo. The setup for the demo is taken from a PhD thesis by James Hall with the title Study of Viscous and Viscoelastic Flows with reference to laminar stirred vessels. So I'll set up the geometry. It's a small vessel. And the baffle width is 1/10 of the diameter The offset from the bottom is 0 in this case, and the diameter of the impeller is 1/3 of the vessel diameter, and it's a Russian turbine in a flat bottom vessel. And this is what it looks like. I'll also define a parameter for the number of revolutions per second. Which is going to be 40 for this simulation. Now, the next step is to add the physics, and in this case we're going to use rotating machinery laminar flow interface. And I'm going to simulate incompressible flow, and in experiments James used silicon oil with a density of 972 and a dynamic viscosity of 1 Pascal second. And now we'll see how to use the selections set up in the geometry subsequences to define the simulation. So we're going to need a rotating domain, and we have predefined selection here, which is called rotating fluid domain. So this is set up here in when we're building the geometry, and we define a parameter n for that, and then we'll add boundary conditions. So we have rotating walls, and that's also a selection in here. We have rotating interior walls. Those are the thin structures, and we have a selection for that. Then the baffles are also modeled as thin immersed structures, so they will be interior walls. And at the top I'll use a symmetry condition. Then the geometry sequence sets up an assembly with the two domains, a rotating domain and a stationary domain. So we need a pair condition for the flow continuity between the two domains. And that's the identity pair defined from the geometry sequence. Now we also need to fix the pressure, so I'll add a pressure point constraint, which is also in here, and I'll just leave that at 0 pascals. Next, we'll import some post-processing variables. So I'll go to definitions and add local variables, which I will import. Now you'll see that there are two definitions here. We have one definition for the thin structures. So on the rotating interior walls, we have one definition, and on the rotating walls we have another definition of the torque. Here's the torque per area. And the reason is that the thin immersed structures have two sides, so you have to take both sides into account. So it's a slit in the geometry, and that's why you have two definitions for the stress, one on the upside and one on the downside, whereas a regular rotating wall only has one definition. And in order to evaluate this, we need to integrate, so we'll add integration operators on one for the rotating interior wall, and then we need another one on the rotating wall. So now we're getting close. Next we need a mesh, and I'll just use the default mesh for the simulation, and for the study type I'll use the frozen rotor study. Let's close this one. So now we're ready, and here we can just press compute. But unfortunately, any 3D simulation takes a while, so I'll switch to the solved solution. Here we see the solution. The Rushton turbine discharges the fluid radially, creating two zonal vortices, one in the upper part and one in the lower part. And a bit of mixing occurs between the two vortices, but less so than within each vortex. This is called compartmentalization, and it's a typical effect of a Rushton turbine. And by the way, the vectors here are in-plane vectors, so we don't see the rotation component. And the colored surface is the magnitude of the velocity. So now let's use our import variables to evaluate the power draw. We'll use a global evaluation, and I'm going to rename this and we have to type in the integration operators. So we had one for the rotating interior walls, and one for the rotating walls. And we can put in description as well. Oh, sorry. And if we evaluate it, we get about 2.9 watts for this case. Now, in the thesis by James Hall, you defined a flow number on a surface, a cylindrical surface surrounding the impeller. So I'll set up a corresponding surface, and we'll add a parameterized surface with the angle and this extension in the vertical direction, which is 1/10 of the impeller diameter, or sorry, 1/5. And it put the radius to be slightly larger than the impeller. So we can see what the surface looks like. Here we see that it surrounds the impeller and it's got the same height. Now we want to integrate the flux on the surface, so I'll add surface integration, and I'll show you how this flow number is defined. So we call it flow number, and it's defined as the flux to the surface divided by the number of revolutions per second times the impeller diameter cubed. So we'll have to put that in. We're going to integrate on the parameterized surface, and we want to integrate. To get Q, we must integrate the radial velocity on that surface. So it's U times cosine of the angle plus V times sine of the angle. And then we want to divide by N and diameter cubed. And we'll call this the flow number. So if we evaluate it, we get 0.56, and it's a non-dimensional number. And I put in the experimental results from the thesis here, and the case we simulated corresponds to the highest Reynolds number. In this case, the highest Reynolds number was 28. And we see that we're indeed very close to the flow number that he obtained experimentally. And we didn't do anything special here. We used the default mesh, and we still, with a frozen rotor study type, we managed to get very good results. So that's always encouraging. So that pretty much concludes my live demo, and we'll go back to the presentation.
Thank you. Yeah, the slide before, I think, because we're going to have another poll question before we get into the Q&A. But now's a good time to type your questions in and send them off to us so that we can I can place them to Mats. But let's just look at this final poll question here. Bit of feedback for us at Comsol, as well as interest to you yourselves, maybe. And it is, can you see a need for the simulation of mixers for your applications? And the possible answers are, well, the functionality in the mixer module will assist my modeling with CFD in general. Not that much into mixing, but I am interested into rotating machinery and rotating domains and the like. The second option is I would occasionally simulate mixers. The third is I would regularly simulate mixers. And the final one is I would not need to simulate rotating fluid flow or anything like that at this stage. So we're looking at a few more seconds here, chance to vote, as you feel. And I'll just close that off now and then share the results with you. And we can see that there's a number of people out there that are interested in the rotating fluid flow and so forth, not necessarily within mixers themselves. And there are a small number of people who are into simulating mixers, and I don't think that's a surprise, is it, Mats, at all? A lot of the machinery within the CFD module as well as the mixer module would be also applicable to many other types of rotating machinery and so forth. So anyway, let's hide that and go back to our presentation here. And this is the chance where you all get to ask questions of Mats and maybe myself. We'll be able to answer them. So just type them in the question or the chat section or so forth that's within your GoToWebinar window there. And I'll start now with our first question. And our first question is, can I have multiple rotating domains within the same model?
Yes, you can, as long as the domains don't intersect. So you can have rotating domains that are connected through some other domain.
Okay. There's a few questions here that may have pointed to a slight fact that people may be slightly confused. But am I correct, Mats, in saying that the example or the demonstration that you showed us was of some type of predefined model where a lot of the parameters were already set up, and that if you changed a parameter number, like you turned it to a 1 or a 2 or whatever, then you were just more or less creating or specifying a new type of mixer, but that the number of possible mixes there was restricted to certain types. Is that correct?
Yes, we have the mixers that are included in that geometry file are flat and dished bottom mixers with either pitched blade impellers or Rushton turbines. And then we have a set of parameters, I think 12 or 13, that you can use to change the shape of the impellers or number of blades and so on. Right. But the model is there to show you how to set up these geometry subsequences so that you can include your own geometry.
Okay.
And how to build it into the to simulation and define the selections that make it easy to set up a simulation.
Okay. So in other words, if you have I have a question here that is, can the mixer module support a mixing vessel with helical impeller and a homogenizer located at the bottom of the vessel. In other words, we can include any basic type of mixer geometry.
Yeah.
Okay.
We have a model that's coming in the model library update with a helical ribbon impeller.
Oh, okay.
And
so to a large extent, people may be able to use some sort of like template model and then change some of the settings to put in their own geometry. But in general, if they had, say, a CAD file, for example, then they could bring that in and model that.
Yeah. The picture we saw from the previous, I can take it back. This one, this geometry comes from this is a CAD geometry that's been imported.
Okay. Okay.
For the impeller.
Right. Here's another question for you. Can we simulate a partially exposed impeller? In other words, that the part of the height of the impeller is submerged while the other part is exposed to the air.
Yeah, we should be able to do that.
If we're doing so, are we actually simulating like two-phase flow or two-phase immiscible flow? Or
no, it won't be two-phase flow. It will be a free surface.
Okay.
So, like, also going back to the picture I showed you before, here we have a model with a free surface. So
okay.
Here there are two cylindrical structures which deform the surface. And I think we also had a movie of that. This one. So you can see the deformation of the free surface due to those.
All right. So if it's a submerged or half-submerged impeller, then the impeller itself would be part of defining or simulating that free surface.
Yeah.
Okay. So here's a more specific or general question, I should say: is that how do we actually go about for modeling those free surfaces? How is a free surface simulated? Maybe you want to go through that slide again.
Oh, which one? This one, or?
How does COMSOL actually model a free surface?
Okay, so we use an alternating Lagrangian Eulerian frame to move the mesh on the surface, and the surface moves because of an imbalance of the surface tension forces. So I think a lot of people are familiar with the static balance, but once that balance is upset, you can define a force from that, and that's how you move the surface.
Okay.
Does that answer the question?
It wasn't my question, so I hope it answers the audience's question. Here's another one. What is the difference between a rotating wall and a rotating interior wall? I think that was, you set that up there during your demo.
Yeah, and the rotating interior wall is a thin immersed structure. So it doesn't have a thickness at all.
Mm-hmm.
And it can be used, for example, we used it in the simulation to model the thin impeller blades, so that we don't have to resolve all the structure of the impeller. And that way we can save some time. And in this case, it seemed to give reasonable results anyway.
Right. Here's another question for you. In what applications would I use the frozen rotor ability feature?
The frozen rotor study type it should always be used when you're looking for a steady solution to a problem where there's no topology change between the rotating domain and stationary domain. And if there is a topology change, it can't give you the correct answer, but it will usually give a reasonable approximation. And it's also very nice to use it to generate initial conditions for a full time-dependent sliding mesh solution.
Mm-hmm. So why would I want to create an initial condition for a rotating mesh solution?
A full sliding mesh solution is it's very time-consuming. So the closer you are to a solution, the faster you will get it to converge. And so if a frozen rotor simulation gives a reasonable result, you can use that as initial condition, and then you will get faster convergence for your sliding mesh solution.
Okay, so in a real mixer, if you like, then I can run the frozen rotor for a while, or quickly, in other words, and then I don't have to go through as many time steps after that.
Yeah.
Okay.
That's true.
Here's a question, what type of meshes are available? Example, unstructured tetrahedral, hexagonal, structured hexagonal?
Yeah, basically all of them. All the meshes that are available in COMSOL are available also in the mixture model.
Does that include boundary layers and stuff? Boundary layer
yeah.
meshes? Okay.
Yeah, boundary layer meshes and structured and unstructured meshes.
And
actually,
in general, which mesh type would you recommend then, or it doesn't really matter?
Well, if it's possible now, if it's possible, it's always or usually better to use a structured mesh. But in many cases you can't do that, like when you have complicated geometries. But I think in this simulation we actually used a swept mesh for part of the geometry, for the upper part, and then we matched or we had a fluid continuity condition to match that to the mesh below, which was unstructured.
Okay. Another question here: can you model a multi-phase flow within the mixer module? I'm not sure. Maybe let's say bubbles or something that are being sparged through the mixture while you're rotating these.
Not truly two-way coupled multi-phase flow. We can model passive scalars now, but this is a feature that we're going to put in for maybe next release or the one after it.
Okay.
We put in a mixture model or a bubbly flow model. So that's something we're working on.
Okay. So another question there about what was it, pulp paper suspensions. That's not something that we would model per se with the solid and fluid abilities. It's something that you'd have to assume the solid particles were just a concentration or something.
Pulp is very difficult to simulate, and so I guess
I believe you
simple way.
That a bit.
Yeah, I worked with pulp for 9 years, but I guess the simplest way is just to try to use one of the non-Newtonian models.
Right.
And if you want to do, it's very difficult because there are no really good models for pulp.
Okay.
But if you settle for a non-Newtonian model, you can use that to simulate pulp.
And do you have the ability to model immiscible two-fluid mixing capabilities? Maybe, I don't know, like maybe oil and water?
And like with a level set model, or
I don't know. How would you do it?
yeah, well, it depends if it's dispersed or if it's large chunks of unmixed fluid. And I guess you could use the levels. You could probably couple the level set method. I have to check on that actually. I think it should be possible.
Right. Going back to the example that you showed, so it's more of a template there for a number or a large number of mixes that are out there. One person has asked, can the model be set up, so I suppose the model template, if we can call it that, can it be set up so as to have default solving methods and outputs? In other words, if someone is to use that and just change the geometry parameters and maybe the fluid parameters as they see fit, do they have to really worry about, you know, the solver or any of that type of stuff? This is a person that doesn't have a CFD background.
Well, I guess as you increase the rotation rate, you increase the Reynolds number. So you have to be, you have to make sure that you resolve the boundary layers. Or if you transition to turbulent flow, you have to switch to turbulence model. But otherwise, it's
so it's just a matter of switching solver. You don't have to go in there and play with the settings or any of that type of stuff.
No, that should be taken care of by those selections.
Yeah. A couple of questions we've had here. Do we have a model for airfoils, or are we thinking of including airfoils in those model templates?
For the mixer module?
Yes. Well, I don't know, maybe the CFD module. I believe that you can have airfoil, or we can have foil type in Pelican.
Yeah, you can have foils in rotating domains. That's often used also in the pulp and paper industry for screens.
Right.
But we don't have a model like that yet. But we're working on expanding the model library for the mixer module.
Okay.
So there will be more models coming, and that's a good point. We can try to put in a model like that.
All right. Another question: can you explain the difference between the K epsilon, Reynolds K epsilon, and the K omega, and tell me when I should use each of them?
Well, the low Reynolds number K epsilon model resolves the flow all the way to the wall, whereas the standard K epsilon model utilizes wall functions to model the flow in the near wall region. So I guess when you need to resolve the layer closest to the wall, so the buffer layer and the viscous sublayer, then you need to use the low Reynolds number model. So, for example, if you have mass transfer at Thai-Schmidt numbers or heat transfer at high Prandtl numbers, you would so that the temperature or mass fraction layer, boundary layer, is thinner than the boundary layer, the momentum boundary layer. Then you need to use the low Reynolds number K epsilon model.
Okay. One final thing here was someone actually asked if we have Caro and we have Power Law, but do we have Herschel Bulkley? which I know that we don't, but you can add your own equations, correct?
Yeah, you can add that on your own. That's also something that we're going to expand on. But we have the user-defined field, so you can type in anything, pretty much.
And this listener's coming actually with some pretty good advice, because he says that Herschel Buckley would be a good model for paper pulp. I suppose when you're asking that question, and he's also said that about 95% of mixers use hydrofoil, so we should definitely look at that.
Yeah.
So I think I'm going to have to wrap up there. We've got 5 minutes left. I just want to tell the audience how they can go further. If you want to switch to the next slide. So I'd like to conclude this webinar by inviting you all to join us at our complimentary hands-on workshops throughout North America, Europe, the rest of the world. At these workshops, you get the chance to play with the software for a couple of hours while being instructed by one of our technical staff. They'll be on hand to answer your questions that relate to your specific applications. And you all come away from these workshops with a trial license of Console and access to our support staff during a 2-week trial period of the software. So it's a great opportunity for you to get a feel for the modeling and what it can do for you. And finally, you can also contact us directly by visiting console.com. If you take the next slide there, Mats. There's a lot more information there. At the model gallery, for example, you can access the model files and documentation for the demo you just saw Mats run. And you can also see this webinar again, or suggest that one of your colleagues checks it out. So thank you all very much for listening. Thank you very much, Mats, for a great presentation and for giving us a great insight into this new product. And I wish you all a very great day. Thank you.